The use of sampling distributions to construct confidence intervals works a little differently from how we use them to perform a hypothesis test. Let's go back to the example recently used. Suppose a team of psychologists, child development experts, applied mathematicians, and educators wisely developed a gadget to give to underprivileged children that would provide the opportunity to acquire literacy skills and other foundational assets, allowing them to excel academically and pursue meaningful careers later in life. So last summer, 36 underprivileged third graders whose reading scores had fallen over the previous summer interacted with the gadget at least 12 hours per week. Their mean reading score at the end of this summer, 4.05. Assume the population standard deviation is 0.8. Construct and interpret a 95% confidence interval for the mean reading score of all underprivileged third graders who would use such a gadget over the summer. Now here's the theory that helps us wrap our brain around the 95% confidence interval. The work we did computing power and type 2 error can help. We don't know the true population mean, but we know this. Whatever it is, it's located in the center of the sampling distribution of infinitely many sample means of size 36 taken from the population. And where should the middle 95% of sample means lie in relation to the center of the distribution? Hey, the empirical rule tells us it's approximately within 2 standard deviations. Remember, 68, 95, 99.7%. But more precisely, 1.96 standard deviations. Remember, that's the z-score that traps 2.5% of the tail. So 95% of all sample means are going to be within 1.96 standard deviations of the true mean. Our sample mean is most likely one of these. Therefore, given the location of our one random sample, there's a 95% chance that the mean is within 1.96 standard deviations of our sample mean. Let's look at the confidence interval formula in the AP formula sheet. Start with our statistic, or sample mean. Add and subtract 1.96 times the standard deviation of one sample mean. This is 0.26, also known as the margin of error. The margin of error due to typical random chance fluctuation. So 4.05 minus the margin of error to 4.05 plus the margin of error, we're 95% confident the true mean is somewhere in that interval. Now here's why. If our sample mean was here, do you see how the true mean is within a margin of error? If it's here, same thing. The true unknown mean was within a margin of error. We don't necessarily know on which side when we take our sample. We just know that 95% of the sample means are going to have this relationship to the population mean. Why are we not 100% confident? Well, 5% of the sample means are victims of bad luck random chance fluctuation. They lie beyond 1.96 standard deviations from the true mean, and conversely, the true mean is more than a margin of error from the sample mean. So, 95% of confidence intervals trap the true mean. Warning, don't picture our sample mean of 4.05 being in the middle of the sampling distribution. It doesn't work that way. The true mean is in the center. So instead, picture it like this. Our sample mean is at 4.05. Here are different ways that the sampling distribution could be oriented, unknown to us, about that 0.05. In each scenario, the mean is within 1.96 standard deviations. Only in extreme cases like this one would the mean be beyond 1.96 standard deviations and therefore not be contained in our confidence interval.